Alright, in this video we're going to look at finding the domain of a function, which we're going to spend quite a bit of time doing throughout the course, throughout the entirety of the course. So as we progress, we're going to look at various functions, many of which are going to have restrictions on what type of input values they will allow. And for right now, our domains for what we're going to talk about here in this section are going to be all real numbers except for two instances, two special types of instances. The first is if we have an even root, like a square root, fourth root, sixth root, eighth root, etc., of a negative number. We're not allowed to do that. So if we have something like a square root of x, x can only be 0 or higher. Or if we have something like the fourth root of x, then x has to be 0 or higher. Odd roots, like cube roots, the domain's all real numbers, but any even roots, like square roots and fourth roots and sixth roots and yada, 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 we cannot take even roots of negative numbers. Also, we are not allowed to divide by 0. So if we see a variable in a denominator, that denominator is always never allowed to equal 0. So always never. That's weird. Yeah, denominator never allowed to equal 0. So as of right now, these are going to be the only two domain issues we're going to see. So if we don't see any of these, then our domain will be all real numbers. And we'll build up more functions throughout the course that have, some of which have special domain restrictions as well. So example 5, find the domain of each. We have g of x is the square root of 4 minus 3x. So here we see a square root, which means the 4 minus 3x inside of it cannot be negative. So we're going to set the 4 minus 3x, which is inside that square root, 4 minus 3x called the radicand, must be greater than or equal to 0 because it's an even root. So we'll subtract 4 from both sides. We'll get negative 3x is greater than or equal to negative 4. Then we're going to divide both sides by this negative 3, which is going to flip our inequality sign around. And we'll get x is less than or equal to 4/3. So we can plug in a value, any value of x we want, as long as that value is 4/3 or less. So if we plug in 0, we'll get the square root of 4, which is 2, and that's okay. But if we try to plug in something like 10, into our calculator, 4 minus 30, the square root of that, it's going to give us an error message. So notation-wise, less than or equal to 4/3 is parenthesis negative infinity, 4/3 with a bracket. So part B, we have h of x is the fifth root of 4 minus 3x. So very similar to the last question, except this time it's the fifth root. And since 5 is an odd number, there's no domain restrictions. We can put any number we want in for x into this function. It'll give us back a number in return. So the domain restrictions, we won't be able to put in any number we want for x. All right, part C, we have a complex fraction, 2 over 1 minus 4x over x minus 3. And we'll be reviewing quite a bit of concepts from your prior math classes in here as well. So complex fractions are nothing more than fractions within fractions. So we see a total of 1, 2 fraction bars. So if it has more than one fraction bar, it's a complex fraction. So first up, we have this denominator, this x minus 3 denominator. That's not allowed to equal 0. So if x minus 3 is not allowed to equal 0, that means x is not allowed to equal 3. So if we plug a 3 in for x into this function, it's going to give us back an error message, like trying to divide by 0 or undefined or something like that. Now, the complex fraction itself, we have this big fraction bar here. This 1 minus 4x over x minus 3 is also a denominator. And to simplify complex fractions, we're going to multiply the big numerator and the big denominator by the least common tiny denominator. So we're going to look at all these tiny denominators here, these tiny fractions like x minus 3, and we're going to multiply our big numerator and big denominator by that tiny denominator. So we'll get more practice throughout the course with dealing with complex fractions. All right, when we do that, on top we get 2 times x minus 3, and then on the bottom, 1 times x minus 3 is this x minus 3, and then bring the minus over, and then 4x over x minus 3, when we multiply that by x minus 3, those cancel out, leaving us with just the 4x. So in this big denominator, we have x minus 3 minus 4x, and that denominator not allowed to equal 0. So x minus 3 minus 4x is not allowed to equal 0. Combine like terms. We get x minus 4x is negative 3x minus 3 can't equal 0. so x can't equal 1. So recapping from this example, part C here, we said x couldn't equal 3 and x couldn't equal -1. So if we have our number line, we'll put holes at -1 and 3 and shade everything else. So reminiscent of the end of the basic set theory and interval notation video. We get this part is -infinity to -1. We're going to unite that with -1 to 3 and unite that with 3 to infinity. So here's our three intervals on the number line. All right, part D, we have the fourth root of 2x plus 1 over x squared minus 1. So quite a bit going on in this one here. First up, the numerator is inside of an even root, so the 2x plus 1 has to be greater than or equal to 0, because we're not allowed to take the fourth root of a negative number. So if we put the 2x plus 1 greater than or equal to 0, we can guarantee that we won't be taking the fourth root of a negative. So subtract 1 and divide by 2, we get x is greater than or equal to -1/2. Now that covers the numerator, but we still have this denominator of x squared minus 1. So with x squared minus 1, that's not allowed to equal 0. X squared minus 1 factors is x plus 1 times x minus 1, so these can't equal 0. Which means that x plus 1 can't equal 0 and x minus 1 can't equal 0. So x is not allowed to equal -1 and x is not allowed to equal +1. So from our two parts of this example 5D, we started with saying that x has to be greater than or equal to -1/2, but it also at the same time cannot equal 1, and the -1 is really not going to have much of an impact here, simply for the fact that here's our greater than or equal to -1/2. -1 isn't even part of it, so it's not really going to have much of an impact, but this 1 will. So we have between -1/2 and 1, not including the 1, and then greater than 1 as our intervals. So we have bracket -1/2 and 1 with a parenthesis. It's this first part here. And then we have 1 to infinity greater than 1 is this part right here. All right, part E, we have r of t equals 4 over 6 minus the square root of t plus 3. Well, first up, we have a t plus 3 inside of an even root, inside of a square root, so it has to be greater than or equal to 0. So t has to be greater than or equal to -3. In addition to that, the denominator, 6 minus the square root of t plus 3, is not allowed to come out to equal 0. So if we add the square root of t plus 3 to both sides, we get 6 not equal to the square root of t plus 3. To free up our t plus 3, we square both sides, and we get 36 can't equal the t plus 3, so t is not allowed to equal 33. So we said t has to be greater than or equal to -3, but it's not allowed to equal 33. So if we graph that on a number line, here's greater than or equal to -3, but let's put a hole in the graph at 33 because it's not allowed to equal it. So we have between -3 and 33, and then we have greater than 33. So between -3 and 33, we have bracket -3 to 33 with a parenthesis afterwards. And we're going to unite that with parenthesis 33 to infinity. And always a parenthesis after infinity. All right, finally, example 5F, we have I of x equals 3x squared over x. Here we have an x in the denominator, and again, we're never allowed to have a 0 in the denominator. So there's only one value of x we're not allowed to plug into this function, and that's x equals 0. So if we have our number line and we put a hole in at 0, we actually saw this in the last group of problems in the basic set theory and interval notation video. We get -infinity 0, unite that with 0 infinity, and parentheses all around. All right, that about does it for this video. Thank you for watching, and I'll see you next time.